not recording yet. Now we're recording. So phase one will be available today officially. It's been available all weekend, and I don't know if anybody's done yet. And it's due in a week, so next Monday, and hopefully we will be able to finish what we need out of chapter 3 today. We'll go through whatever we need from chapter 1 in just a second. And let's see, Ben is here. The other Ben is currently in the air, flying back from Texas, so we don't have to make a pilgrimage to Texas to get him back. He's coming of his own free will, which is good, because it's a long drive to Texas. I believe Ben posted something on I wanted to say Yap, but I didn't mean Yap because I posted something on Yap, Canvas, right?
Yeah, on Canvas.
Okay, and basically there was some misunderstanding, let's call it that, between somebody in class and me this morning about what we were allowed to do with respect to. I'm out of Pepsi. I don't have any more. What you're allowed to do with when you're retaking the course. If you are retaking the course, you must delete everything you have and start over as if you didn't take the course last semester. So, and also, if you are retaking the course and you want to not do the project again because you want to transfer your grades, do let Ben Sofson know and CC me on it as well. I don't know, Ben, if you've heard from everybody yet as to whether or not they want to retake or transfer grades. But if you're retaking, please let Ben know what your situation is going to be.
Yeah, you can either let me know now or at the end of the semester. For those who are retaking and want to transfer over grades, you can let me know now, but I won't be handling it until the end of the semester. That way, like at the end of the semester, when I see just a blank row of your grades, I'm probably...
Oh, you cut out there. But yeah, just let us know. Right. Any questions that we need to deal with, or can we get going? I'll grease up here. And when will phase 2 be open? Monday night next week. Because phase 2 has phase 1 solution in it, so therefore I can't give you that one until phase 1 is handed in and closed off. And I suppose you really have to get your act together and group up. To make groups and let Ben know before Monday next week, because you can't hand in until you've made your groups if you're going to be working in groups. Anything else? All right. Well, in that case, let's get going. So I want to try this, and I know I haven't taught 326 for a long time, so you might not have seen this one before. Although I have a feeling that Ben might have thrown something like this at you, but I just oh, hold on. Says, do we send in the discussion forum to let Ben know if we're working in groups? Send him an email, I would assume, or a message.
No, you're going to send me a message on Canvas, yeah.
Message on Canvas. Okay, very good. Very good. I almost flooded your email box there. Sorry.
Please no.
All right, I'll keep my big mouth shut, and we'll move on to something else then. So this is example. We're really starting from the very beginning, and the idea here is really, I just want you to consider this, and hopefully this will explain why it might be a good idea to know something about a language in somewhat greater detail than you get from just reading a manual, and maybe having an understanding of how a compiler works and how it's implemented actually does give you a better idea of how to program in a nice way, or in a safe and more secure way, rather than writing sort of nonsense code. So I'm just going to write this down. And then we'll talk about it. So we get something like this. And then the question of course is, what is the value of A at the end, and here the value of B at the end, and at the end here I mean at the end of that line. So take a second, don't type it in, see if you can get this right, and somebody tell me if they saw something similar in Ben's class. Yeah, you did that in his class as well. All right. Well, then you can't get it wrong now. I am recording. I'm pretty sure. Recording is in progress. Open the recorder to manage recording. Yes, we are. Well, yeah, this is example 1.1 in the book, so you can actually look up the answer there. But try doing it without looking it up, just to see how see whether or not you're going to be allowed to use the plus plus operator in future in the future of your programming career. Because if you get it wrong, you're not allowed to use that one anymore. So have we got any I don't want to say guesses because that's not what they should be, but have we got any suggestions, any answers for what A and B might be? Then I shall write them down if we. So Jonathan says 23 for this one. And this one, no, for the first one. And Amy says 24 for that one and 24 for that one. Shouldn't it depend on the language too? Possibly, yeah. It depends. I mean, what we really probably should do is we should try to well, maybe can we make a list here? What affects the result? So what things could affect the result here? I think Amy is right. It depends on the language, but what particular language constructs would I need to know and understand in order to answer the question correctly? Whether or not increment is applied before or after assignment, right? So is post increment applied before assignment? Yeah. And maybe also is it left to right or right to left? Evaluation. Now, surely the post inc, this one here, is very important. Is this sort of stuff important in general for evaluating expressions? So do I have to consider whether or not? No, I should consider whether or not I can spell left. Do I have to consider whether a language is left to right or right to left under all circumstances, or does it not really matter? Anybody got any? Does it scan left to right? Well, that probably doesn't matter too much now. I'm more thinking about, when you look at this, do you do the evaluation in the order of first that one, then this one, then this one, or do you do this one, this one, this one, or does it matter? So does it matter in general? And I think the answer to that is it only matters if there are side effects. So just evaluating a variable, looking up the value of a variable, so for example this one here, you can do that as many times as you want, and you can do it in whichever order you want. So if your expression consists of nothing but variables and constants, whether you evaluate it left to right or right to left, doesn't really matter, because you're still going to stick by the rules of evaluation where you do multiplication before plus, etc., etc. But here we do have something that has a side effect, which is this plus plus stuff. So here, the order of evaluation might actually matter. So we're going to say, assume left to right evaluation. All right, that's just because that's normally what we do. That seems like to be a reasonable thing. We still have to figure out whether that post-inc is applied before or after the assignment. So in general, if I look at this, is this post-inc is that executed when I'm done with just this part, or is it done when I'm done with that entire part? Well, it might not be that this is part of an assignment. So in general, we should probably ask, is the post increment done after the entire expression is evaluated or after this is done? And I think it probably makes more sense to say that the post increment is done when the particular part that it's applied to has been evaluated. So let's go with that. So we can say, right, we'll get 7 here because a is equal to 7. Then it gets updated to 8. Then we get 8 here. Now we have a plus plus, so that means this gets updated to 9, and we get a 9 there. So we get 1524. There we go, right? So now we start over again. We get a 7 here. That becomes 8. We get an 8 here. Then this becomes 9, and we get a 9 here, and we get 24. Well, that was whether that's good or bad, I don't know. In Java and PHP, the value is 24. I did have versions of C and C++ where the value of A was 23. So 23 in some versions of C, C++, and 22 down here. I think those might have been mistakes in the compiler. It could certainly have been the way that they wanted it. I don't know. But we got to be careful when we code something very similar or very simple like this, because, you know, how dangerous is it to use a plus plus? Well, if we don't know what the semantics of it is, then maybe we shouldn't be writing stuff like this. And today, most compilers are smart enough to do optimizations for us. So try not necessarily to be smart in doing arithmetic and stuff like this. You know, rather take a line more and be explicit about what you really want. Which leads us to the syntax versus semantics, which I know you've talked about a million times. So what's the definition of syntax? And what's the definition of semantics? So here I'm talking in terms of what is the syntax of a language? Yeah. So Zach says the rules defining what strings are members of the language. That's hard and cold, the definition, right? We'll write it down. So this is the the rules defining which strings programs are members of the language. Now we could start asking questions and say, what do you mean are members of the language? Because there are some programs that might be syntactically correct, but have some other issues that all of a sudden means that they're not really a member of the language. So I think we could say something like programs that can be generated using the formal grammar for the language. Okay. What's semantics then? I think you probably, if I were to, yeah, so the meaning of the programs in the language. So the meaning of So I'm going to say the meaning of the various parts of a syntactically correct program. Because there's no point in talking about the semantics of a syntactically incorrect program. So this could be things like how to evaluate expressions, how to evaluate statements, possibly by rewriting, etc. So I think you've seen these before, so let's not dwell too much on that. You've probably seen this other stuff as well, so let's just see, how do I do this? Can never remember. There we go. Aha. So I want to insert this one here. And now that we're at it, we might as well grab this one. We'll put that one over here. Just make it a little smaller. There we go. So I have these two pictures here. One is of an interpreter, which I suppose we could put up here. And you've seen these things a million times as well. An interpreter is something that takes in source code and data, munches on it, and produces output and errors. So this part here is something that executes this. And you wrote one of these in 326 if you did it with Ben. You wrote an interpreter for Java bytecode, right? So you have a pretty good idea of what it does. You know, this thing has to maintain things on the stack and on the heap and execute all the instructions or the statements, evaluate all the expressions using certain rules, right? So you're sort of knee-deep, high in semantics, because you have to look at the semantics of all these various instructions in order to get it right. Whereas in the compiler world, it's really more of a translation. We take a source code program, and we produce a target code program, which then can be run on some hardware or alternatively run in an interpreted manner, just like we saw with the Espresso output. So the Espresso compiler, which is what we're writing now, will produce EVM code, which is Java bytecode, and you've written the Java virtual machine, Espresso virtual machine, to produce or to handle executing that. Right. Fair enough. Now, if we take this guy here and zoom in a bit, then we get something that looks like this. So imagine this being a compiler for some language L, where it takes in programs written in L here and spits out programs in another language or representation here. Then there are sort of two distinct parts to a compiler. There's the front end and there's the back end, where the front end is primarily concerned with syntax analysis, some semantic analysis, and the back end is primarily concerned with the translation. And we can have very many different small stages here, and we might have some sort of internal representation where when the front end is finished, it produces an internal representation, and that is passed to the back end, and then it works off of that. So this could be a syntax tree of sort, which it typically is. Now, the reason that it might be nice to have one of these is because, think about the following. If you have a whole bunch of different languages and a whole bunch of different architectures, so we might have something that looks like this. So we have N languages and M architectures. Then each one of these lines is a compiler that compiles from this language to that architecture. That's this guy. So here we have something like N times M compilers. But if we introduce, so it's the backend code generation. Yes, it is. It's definitely a backend thing. If we introduce an internal representation, or an intermediate representation, then we get something that might look like this. So again, we have our N languages and M architectures. If we can find some sort of intermediate representation or intermediate language, if you wish, that we can use to represent all of these different languages internally, then now we can get away with just implementing N front ends and M back ends. And as I said, that internal representation, intermediate representation, can be anything that might be useful. And what we'll use is a, so here we get N plus M, but I don't want to say N plus M compilers because they're just half compilers, right? So it's half of one and half of one in some way. Now, if we look at the stages of a typical compiler, and this is by no means gospel, but it seems like a reasonable approach, then we might have something that looks like this. So we have a source program that comes in at the top. We do some sort of lexical analysis, and what comes out of here is typically, actually, let's just quickly talk about what goes in here. And I want to describe this as a stream of characters. So basically, it's just a long stream of characters. Bernard, you might want to turn your camera off or get dressed. This is why you always remember to put your pants and your jacket on before, or your t-shirt on before. Well, It happens. Just not to me, because I know. But anyways, no harm, no foul. We didn't see your butt. So a stream of characters is just sort of a flat thing, right? You can think of a file as just a long string, an unordered. Well, it's an ordered, but it's just a long flat string of characters. There's no structure to it. So what I want Lexical Analyzer to do is I want to create just a little bit of structure, which is I want keywords and identifiers and semicolons and things like that. I want those identified. So what I'm going to get out of this is a stream of tokens. So the structure is at the level of keywords, variables, or actually should we just say identifiers? Etc. However, it's still flat, right? So I've just basically taken this long stream of characters. We don't capture face cams. No, we don't capture anything except from, I don't know, me maybe. I don't know if my beautiful mug turns up on the recording. No? Aw. So this is not how I'm gonna get discovered and become a YouTube star and quit this racket. I guess the strip is still my best. My best option then. Just a faceless voice. That's disappointing. Well, anyways, so what I have now is still a flat stream of stuff, which is now just sort of in chunks of tokens, right? The syntax analysis, then we could send out the same flat stream of tokens, but that's really, really hard to work on. So typically what we get here is a parse tree. So it's a tree-like, or a tree structure, like we know trees from regular data structures. Now, here, it's typically the parse tree again, maybe rewritten or changed a little bit. What do we get here? Well, it's a code of some sort. Could be a stream of instructions. And the same here, and probably the same down here. It all depends on what you want your compiler to do and how you want to implement it. Now, all the rest of chapter 1, just give it a quick read through. I don't want to talk any more about it. There's nothing complicated here. I really want to get started with something important. Not that this isn't important. Chapter 2, you have already done, hopefully, last year or whenever you took 456. As I said last time, chapter 2 is just recap of 4, 5, 6. Read if needed. Which means that we can skip all the way to chapter 3. Which is lexical analysis. So it's scanning and tokenization. Right. So I think I have that picture as well. Let's see if I can find it. I do. So take a look at this little picture here, which is basically the work of a scanner. Okay, so what we have over here, this is sort of flowing this way because that way I can still write things left to right. This is a stream of characters, so this is our program. And the job of the scanner is, as you can see the program was a for loop that said for open bracket I equals 0 semicolon I less than 100 semicolon I plus plus close bracket and more stuff. And what I want the scanner to do is to say, right, I'm going to gobble up some characters until I recognize that what I have here is the keyword for. And I'm going to create a token that is of type 4. The lexeme, which is the actual characters that we got off of the input, is FOR. You can see that there. It was line 37 and column 54. Next one is just this sole left paren. We call that one L paren, with some funny spacing there. And what we really scanned was just this one character. It was line 37, column 58. So it's the scanner's job to take this and turn it into tokens. And if we want to continue tokenizing this, we get a division point here, 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 and here. And we can write the scanners, the tokenizers, so that we don't worry about the spaces. So, for example, this guy here would be a token dot int lit, because it's integer literal. The lexeme is 100, and the line, I don't know, 37. Column, you can guess yourself. So basically, what we need to do is, for a language, if we want to write a compiler, we have to start with a scanner. So we have to go through our grammar of the language and find out what are the various different tokens I can have. If I look at this, we have the keyword for, the left paren, variable name, so identifiers, equal, integer literals, semicolons, there's another identifier, less than, another integer literal, semicolon again, another identifier, the plus plus operator, the right round parentheses. So we need to make a list of all of those. And it turns out that all tokens can be specified by a regular expression, and that I'd like to try to argue that, just so that it isn't something I'm throwing out there. So any token can be specified by a regular expression. So we can just sort of try to go through them. I'm not going to go through all and everything, but let's try some operators like plus, for example. What's the regular expression for a plus symbol? So in other words, can you write a yeah, it's a plus. So that's easy. What about minus? Well, it's minus. What about separators? What's that one? Well, that's that one. And so on and so forth. So all these, we should have a semicolon as well, and it's just that. All right, no problem, right? What is the regular expression for? Actually, you know what I'm going to do? I'm going to put these in like that. What's the regular expression for if? Well, it's the keyword itself. All right. So we can do the operators, we can do the separators, we can do all the keywords. What's left? Well, there are two things left that are a little more complicated than this. We still have identifiers, and literals. So it's not just floating and integer literals, it's all the strings and the characters and the booleans and all the various literal values that we might want. But let's start with the identifiers, because I bet you're familiar with that one from previous courses. Because what are the rules? What are the rules for an identifier? So I'm just going to write those up here. And now Amy can say, well, that depends on the language, and she would be right. So it has to start with a character in almost all cases. Well, that's we could make some very simple rules. We could just say all identifiers are single character, letters A through Z, lowercase or uppercase. That would only give you very few identifiers, so that might not be good. So we might say something like, oh, well, it has to start with a character, or an underscore, or a dollar, or something. So let's just pick something simple. We'll do this for a simple identifier. I'm not going to make it complicated. And we'll go with must start with a character, possibly followed by other characters or digits. That's a very simple one. Can we write a regular expression that expresses that stuff that I wrote in green? A through C, A through Z, something, something. Yeah. All right. So I'm going to do it slightly different. I'm going to say, well, it's an A or a B or dot 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 or a Z or a capital A or dot 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 or a capital Z. So pick one of those, and after that, you can do as many of them as you want. Oops. And that one here is 0 or more times. So something like that, right? Now you can make that as complicated as you actually want, but that's reasonable. What about literals? I don't know. Let's do the Boolean ones first. What about the Boolean literals? What are the Boolean literals? True and false. Remember that when you do your scanner. There are two Boolean literals. There are true and false. Well, that's easy enough. True or false. There we go. What does an integer literal look like? 1, 2. If you keep counting, I'm going to leave. So Zach says 0 through to 9. So choice between 0 through to 9, 0 more times. All right, so that could generate 0, 0, 0, 0, 0, 0. But that might be fine. So it's 1 or more zeros through to 9. So then somebody might say, well, then you can start like 0007 or whatever, but that's probably fine. All right, so fair enough. An integer literal is 0 through to 9. And we'll do a plus. That one means 1 or more. What about floating point? Let's not get carried away. Right. So if we go and look this up, then it's really, really complicated, especially if we want, scientific notation and all this stuff as well. And it actually turns out that I've done these literals for you in the handout because they can be I've done most of them. I've done the integers and the floating points because the scanner we want should also be able to deal with. Yeah, well, Zach, the 0 through to 9 plus optional dot 0 through to 9 star is not enough because there are some other things with exponential, with scientific notation, and it all gets very complicated, right? So I've done that one, and I've just plunked it in for you, and you can use it as it is. There's a definition section in the flex file, which you will see, and I've already defined them in there, and I didn't do it. I just nicked it from an existing Java implementation because you know how it is with regular expressions. They can be difficult. Right. So hopefully we can see here. So let's say hard, but doable. So hopefully this sort of approach shows you that it is probably reasonable to say that the leximes of all possible tokens can be specified by a regular expression. So now the next question is, how do we get from regular expressions to scanners? Well, the first step is all regular expressions have corresponding NFAs or DFAs as you want. NFAs are a little easier. Did you in 456 look at an algorithm for converting, or actually for creating an appropriate NFA or DFA based on a regular expression? I have a feeling you probably didn't. So I want to do that. And it's called Thompson's construction algorithm. Now, just as sort of an aside, I'm going to do that here. And I'm going to ask you the following. Prove that any regular expression is also context-free. How do you do that? Do I need to find the, hold on. Oh, I don't have it anymore. Or do I? I'll look while you think. Maybe it's under utilities. Ah, here it is. Can you hear it? Anyways. Right. So Zach says, show that it generates a regular language which itself is a context-free language. No. That's regular reasoning. No. I'm asking you to prove that any regular expression is also context-free. You cannot use the fact that any context-free language includes a regular expression. I'm asking you to prove that. So basically, you are relying on this one here, right? And I'm asking you, show me that that's true. So how do you do that? Imagine that you were imprisoned on the second floor of the building and you could only get out when you've proven this. How would you go ahead doing it? P.S. The second floor is not very nice. You'd read the book. It's not in the book, is it? No? Well, you don't get to take any books. They don't take you to the library first. And you can't phone a friend. Yeah, you're in trouble. Well, so here's something we could do, and I think, I don't know if you've seen this before, but let me just ask this. So what makes up a regular expression? Well, you can't form an NFA for the grammar because I'm asking you basically if, how do you, we'll get to in a second how you do that NFA, but that doesn't prove anything. Now you have an NFA. What does that NFA represent? We don't know. I'm asking you to prove that NFA could be implemented as a context-free grammar. Because what we want to know is that any regular expression is also context-free. I'm going to tell you something in a second that you probably didn't realize that you probably knew if you thought about it. That sounds complicated and convoluted, but I think it's kind of interesting. So what makes up a regular expression? What is the simplest one you can think of? The simplest regular expression that you can ever make? A single symbol? Anything simpler than a single symbol? An empty. Not an empty set, the empty string. So epsilon, the empty string. Right, and then A in sigma. That's the single symbol. So the simplest regular expressions I can make are empty strings and single symbols. Can I combine those to make more complicated or complex regular expressions? Yes, I can. There are 3 rules. There's concatenation. So if S and T are regular expressions, then S concatenated with T is also a regular expression. I can do choice. If S and T are regular expressions, then S or T is also a regular expression. And then repetition. If S is a regular expression, then S star is also a regular expression. All right. Well, so the star we have here, the plus, is really not needed because what is plus? So S plus is really just S concatenated with S star. So we really only need those 3, right? Now, if I could show how to generate those 5 different things in terms of a context-free grammar, then haven't I proven how to translate any regular expression into a context-free grammar, and thereby proven that any regular expression is also context-free? And the answer to that, of course, is yes, you have. Right. So let's crack on with that. What does a context-free grammar look like for an epsilon? Well, it's just, we'll go with S goes to epsilon. Okay. Can we do a similar thing with any single symbol or singleton? Yeah, probably. S goes to A. How do I do concatenation? Well, if S goes to something and T goes to something, S is the context-free grammar for little s, and T is the context-free grammar for little t, then surely A goes to ST is the correct concatenation. And the choice one is just that. And what does repetition look like? That's the only one where we kind of have to think a little bit. So star is 0 or more. Can I write a context-free grammar that repeats S 0 or more times? Well, yes, I can. It's either S, A, or epsilon, or A goes to A, S, or epsilon. You agree? So what have we got here now? We've got a translation from regular expression to context-free grammar. By simply following these translation rules here. And the interesting thing about this is the shape of these, because what can I see in terms of the A here? Well, I don't care whether I use this one or this one, because I get the same result. I get as many S's as I want. But this one here is right recursive, and this one here is left recursive. So let that think in for a second, and now I'm going to go to the next page, and I'm going to ask you a question. Ready? So now I'm going to ask, is A, N, B, N, N greater than or equal to 0? A regular language. It is not. And when I ask you, so now I'm going to do a little prediction. When I ask you, why not? Then you're going to say something along the lines, you can't count, you need a counter, there's no stack, and some of you might shout pumping lemma, or something like that. Is that what you would say? I'll take that to silence as a yes. Nobody can remember how to do this with the pumping lemma. But what does a context-free grammar look like for this? Now this might be a little bit of a stretch, but it looks something like S goes to A, S, B, or epsilon. Can that grammar be done in any different way? The answer is no, it couldn't. But let me ask you this. Is it possible that that grammar is generated by applying the rules on the previous page to a regular expression? So can this red context-free grammar here be the result of me applying those green rules on the previous page to some magic regular expression that implements a to the power of n, b to the power of n? While you think about that, just think about the following. What is it about this grammar that makes it work? Well, it makes it work in such a way that every time I recurse on S, I get an A and a B, right? So I always get the same number of A's and B's. An A, something in the middle, and a B. And the thing in the middle is something that has either nothing in or a similar number of A's and B's. So why is it not possible that this red stuff here is the result of applying these rules? Well, let's just consider this. I don't know what that is. Let's just consider these. Let's consider this again. There's recursion, right? There's some recursion here. So let's just. So let's just take a quick look at these guys here. Let's see. No recursion, no recursion, no recursion, no recursion. Here's recursion. So the only rule that has recursion is the repetition one. That kind of fits with the A and B N business, right? What does this recursion look like? It's either all the way to the right or all the way to the left. There's no way I can produce a result using this red rule that has something both on the left and on the right of the recursive variable. So either there's nothing on the right or there's nothing on the left. But look here. There's something there and there's something there. So we can certainly say that no rule from the previous page would create this grammar. What does that mean? Well, that means that there exists languages that are context-free, but not regular. So in other words, there are my regular expressions, and there's my context-free grammars, and there are stuff out here. So those two are not the same. I don't think you probably ever thought about this in this exact manner. But I think it makes a lot more sense than just, pumping lemma and wavy arms and hands and what have we not. Something else that's interesting that we really should be talking about the other stuff, but I think this is interesting, hopefully, and I just want to say it. No context-free grammar generated from a regular expression has anything but immediate recursion. That is never the following. So you'd never be able to generate a grammar that looks like this. It's regular, so it's context-free though. It's perfectly fine to have mutual recursion in a context-free grammar. Why can't you generate this using the rules on the previous page? Well, let's see. That doesn't create recursion, that doesn't create recursion, this doesn't create recursion, that doesn't create recursion. This is the only thing that creates recursion, and it always recurses on itself. And if I look at them, this doesn't rely on anything else, this doesn't rely on anything else, this one relies only on things that are defined above it, this one relies only on things that are defined above it, these only rely on things that are defined above or itself. So we cannot create that pattern there either. So if a grammar has only immediate left recursion, so this wasn't there, or immediate right recursion, that isn't there, and no mutual recursion like that, then that grammar is regular. So it can go the other way as well. But if it exhibits this or this sort of stuff, then it's a no-go. Did you know this? No. You do. Right. So now we can go back to asking the question, how does this Thompson's construction algorithm work? Well, we could do the same thing here, couldn't we? There are only 1, 2, 3, 4, 5 rules. What if I figure out a way to translate this into an NFA? Then we can just use the rules on that. All right, easy enough. Let's see. We'll start with epsilon. What does the corresponding NFA for epsilon look like? Well, I have prepared a rather large picture. It looks like that. It can take an epsilon transition to a state that accepts. Okay, what about What about that? Well, that's not rocket science either, is it? It looks something like that, right? We start in a state, starting state, and then we can transition on A to an accepting state. All right, those were the easy ones. I'm just going to go over here, and then we will say S or T. So we need the NFA of S or T. Now, I'm going to refer to N of S and N of T as the respective NFAs for S and T. And if I do that, we get something that looks like this. So let's just take a quick look at that. That's S turned into an NFA, and this is T turned into an NFA. This used to have one of these on, this used to have one of those on. So this used to be the start state for S, and this used to be the start state for T. Now they've turned into just regular states, and this used to be the accepting state, so did this, and we've turned them into regular states, thrown into epsilon transitions to a shared accepting state here, and created a new start state here with epsilon transitions there. So I don't think anybody has any issues with that. And let's see, what does N of S concatenated with T look like? Well, so what would it look like? Well, it would be this guy here with the start state there, and then this one here overlapping with this one, start state removed, and this one here being final. What the hell? So we can see we retained the start state here. This thing here lost its final state value from there and its final state status, so its start state status from there, and we retain the final state status there. All right, that leaves just one. S star. It's got to be something with a blob like this, which you can completely bypass, or you can go through and then try again. So you get sort of this UFO thing here. So here we look at N of S star. Right, so let's take a look at that one. We start here. We can do 0 repetitions and just sort of get around NFS. Or we can go in here and do one version and then out, or one round and then out, or we can go around, try another one and out, or we can go around, try another one and then out. So we get this this UFO looking thing. So now I've given you rules for what all of the constructs in a regular expression would look like as NFAs. So now let's give it a go. So example 3.1. Let's say I have A, B, or B, C, C star. That's a repetition thing with a choice with some concatenation on the inside. All right. Let's start with N of A. Let's see if I have a picture of that, or if I have to do this by hand. I actually have them right here. I'll put them there. So there's N of A and N of B. So now we can do the concatenation AB. That's just going to be like a long string with an A and a B. And we can do BCC, which is going to be a longer string with BCC on the along the edge. So we get something that looks like like this. So you can see here that in order to accept A, B, we do start state to an A, to a B, and then we have accepting. And for BCC, it's BCC, and we're there. Okay, so now I have that part and that part. Now I got to do this part. So the choice one was just to do that. So that's not too bad either. That's this guy. Yeah. So that either goes this way, does A, B, and finishes, or this one does B, C, C, and finishes. So now this just have to be the interior of a UFO, because we're going to do that as many times as we want. So we end up with something crazy like this. So we can choose to do nothing, or we can choose to go in here. Now I have to do something. I either got to go this way or this way, and I can do one and finish, come around, do another, finish, and so on and so forth. So I can take every single regular expression and I can turn them automatically into an NFA. Right. So what we can do is we can say for each token of a language, T1, Tn, create N of Ti. Okay, so now I have a whole bunch of all these NFAs floating around. Well, what I want is I want a regular expression for all my tokens. Well, that's easy enough. T1 or T2 ... or Tn is the regular expression for all the tokens, right? Because if you can match the input to any of those, then you can get a token, right? What does n of T1 ... Tn look like? Well, that's easy enough. We know how to do that, and I might even have a prepared one. It looks like this, right? So go and make my, oh, sorry, you know what? I'm going to call these T's instead. There we go. That's easier to fix those than have to go back and fix the other ones. So now we got something that looks like that. And that's fine, except now we've sort of created another problem. And that is, let's see, let's go back to here. Can I create an identifier that's called if? So can I use these rules to create that? Well, the answer is yes, you can, because you pick an I here, somewhere there, and then you pick an F here, that's somewhere there, and then you're done. So it is possible that all the keywords can be generated using the rule for the identifiers. Well, I have to prevent it from happening, possibly. Yes, that's right. But that doesn't change the fact that the way I have the rules here, I can do that. All right. So now go back and look at this guy. Let's assume that this one here is the one for if, and let's assume that this is the one for the identifier. So if I see if on the input, where would I end up? Would I end up in this situation, or would I end up in that situation? Well, I don't know, because look, this is an NFA. So NFAs are not all that good. Have you ever tried implementing an NFA? And the answer is probably hell no, because it's way too complicated. Because you have to deal with backtracking, right? So we can definitely say NFAs are hard to implement. So we need DFAs, plus don't forget the if as a keyword or identifier issue. So if we could turn this NFA into a DFA, and we could sort of solve this problem with the keywords overlapping with identifiers, then I think we would have an automaton, a DFA, that we can actually use to tokenize input with. What we do is we set it loose on the input. If it gets to an accepting state, we produce the token, reset back to the state 0, let it go on the rest of the input, and then just crank it over and over and over again, and it'll produce a stream of tokens. So there are some issues we gotta deal with. We'll do that on Wednesday, which is, how do I turn the NFA into a DFA? How do I create the right tokens at the right places? How do I get as an efficient DFA as possible? How do I encode a scanning DFA? And how do I implement it? 4 or 5 or however many good questions that was. None of them complicated. We can sort it out next time. Phase 1 is up, ready to go. Watch the video. It tells you everything you need. Don't look at anybody else's code, including your own from previous semesters. Let's see if we can get through this with no stupid cheating cases and no epsilons and follow sets. I'll say this every time. Don't look at your own even from this semester. Yeah, no, you can look at your own from this semester. That's going to help you. Right, so that's it, and that's that. It's 5:15. Good timing. Any questions while I send this to Ben?
Yes, I do have a question.
Okay.
I can't figure out how to log into the Java server that's on to actually download the files for the project.
Do you not have a Bobby password?
No, I don't know how to get a password.
Have you not had a password before?
No, I never logged into the server before.
Oh, well, you need to go to Tux and apply for one.
Go to where?
Tux.cs.unlv.edu, I believe. Hold on.
Okay, I might.
tux.cs.unlv.edu. And what I would do is I would Ben, put it, look in the chat. And what you need to do is you need to, are you going to be developing on your own machine, or are you going to be using the systems here at UNLV to work on?
My own computer.
Okay, then what you can do is, if you can't get an account, you probably won't be able to get an account right now. If you've never gone onto Sally or Bobby, or how did you do 370 without going onto Cardiac?
Wait, which class was 370?
They don't really use Cardiac anymore for those. It's all on VMs nowadays.
Fine. So, is there a way we can get you the tar
I
file?
can get him the source code if he doesn't have it by, say, like tomorrow, for phase 1.
Yes. So if you could go and apply for an account with the link there, and if it hasn't come through by tomorrow, contact Ben and he will get you a tar file and explain to you how to untar it, and then we will we'll sort out with install scripts and when you can get them. Well, no,
Yeah, Zach, he does just need the Espresso script. The problem is the Espresso script requests your login information to the server.
Exactly. So we needed some way of getting him the tar file that the Espresso script goes and grabs, and then give him information on how to install it correctly. Because it's not a problem emailing him the script. The problem is that it's going to ask for a password, and then you're going to be in trouble.
Yeah.
So try to get an account. If you can't get one in time for tomorrow or sometime, send Ben an email. He'll help you out. Thank you, Ben.
Uh-huh. So, guys, the groups are made for everyone that has let me know that they want to be in groups. If you want to, I will not open the submission for phase one until like Wednesday night, because there's problems if I make a whole bunch of Canvas problems. I need to have all the groups first before I make the assignment submission. So right now it's about a 50-50 split, which is about the normal, but I remember the less projects I have to grade, the quicker I can get them done, the happier I am.
I think honestly, it is a real good idea to find yourself a partner,
And the easier it is for you guys.
yeah, it's not a big deal in the beginning, but it gets a little harder later on, doesn't it?
Yes.
Plus,
So
it's
if
always nice
there
to have
is
somebody to
Hmm,
bounce things off with as well, right?
yeah, and if there is any problems with your group, let me know. You can find them in the People tab of Canvas
What the problems?
under Espresso Groups.
Oh, the groups. I'm just being stupid. I'm gonna leave.
Yeah, phase one will be due next Monday at 11:59 at night.
Is
Yes,
WSL?
WSL will be good
No,
enough.
no idea what that is.
Yeah, WSL will work. Just make sure that your Java version is Java 1.8. There are some Linux tools that allow you to dynamically switch your Java version. Just make sure that you're compiling with the right Java version.
Okay, let me just say a few things. First thing
Yes,
is
on Canvas.
first thing is if you are doing weird stuff and using strange tools, make sure that it doesn't insert strange imports into your code
Oh
for you.
God.
If it
Right.
does and we can't compile it, it's your problem, not ours. Second of all, if you do work on it, and you don't feel comfortable that it works, then all you have to do is transport that tar file that the system creates for your hand-in onto Java or Bobby or Sally or whatever, untar it, type ant and see if it still compiles and test it on one or two things. And if it does, then it's good to hand in.
Yeah.
But I think
So
definitely I would
if
do
you're
that.
using an IDE like BlueJ or Visual Studio or anything like that, sometimes they will inject. I think in the past I've seen Sun repositories
Yes.
and Javalang repositories, all this kind of garbage,
Yep.
to fix whatever errors they think they're detecting. And then when it gets to my machine, it just explodes. I know how to fix it, but I will not be fixing it. The first two phases I'll be lenient on, but past that point, no. If I see it and it's in your submission, immediate 0.
If you have a fork, you might as well just stab yourself now. That's how it's gonna be. It sounds like.
Yeah.
And they say I'm not the
Oh,
nice one.
right. And if your code doesn't build, that's an immediate 0.
Don't.
It's the same way as your normal. Yeah, have I given enough context clues? Um, it's the same as your code not compiling in prior classes. If it doesn't compile, it can't be run. There's no more of this, oh, you gave it an attempt, partial points.
Just remember,
If you
you're all welcome to come to his PhD defense later this year. No, no, you're right. I mean,
just get your code building. If it builds, then I can test it and give you the partial points.
yeah, and the reason, let me just say, it's not because we don't want to look at your code and help you. It's because the class size has exploded in size. So if we had to, in the old days when I used to TA this course a million years ago, I would fix up people's code until it ran perfectly, and then the amount of time I would spend on doing that was proportional to what I took off for a grade. But we cannot do that with 90, 100 people. So we have to automate the testing. So whatever runs, whatever doesn't run, doesn't run, and so that's just the way it is, and you know it by now. So make sure you don't hand in code that doesn't compile. Elizabeth, IntelliJ is fine. You can use anything as long as it doesn't inject weird stuff in. So that's why I think whenever you use these fancy environments, just a good idea to upload the tar file, untar it, tar xvf file name, and try to compile it and clean ant and run it on a couple of tests. Yeah, now we're way over time, and it's not my fault this time. It's all you people's fault. So you can't fault me on this one. So I will see you guys on Wednesday, unless you come by. Oh, remember, before you leave, I want to see and talk to everybody. I want to see your beautiful faces on camera once during office hours, preferably earlier than later. Plus, I want to sort of like look you in the eyes and say, "Don't cheat," so that I know that you've seen my the fire in my eyes. So come by for 5 minutes during office hours with your partner, and I'll cross you off. Oh, you have no idea, Nathan. And I'll cross you off on my list so that I don't have to come and haunt you later on. All right, I'm out of here. So are you. See you later. Tomorrow, Wednesday, whenever. Bye.